Hi, today I want to talk about rules of inference in symbolic logic. So a rule of inference is a rule that lets you deduce new statements from old statements. And I'm going to start out with a very classic example. So here is an example. I have statements P and Q. And suppose I know that P implies Q. Suppose I also know that not P implies Q. Well, from that, what can we conclude? This is something you could think about just in maybe the context, not even of mathematical discourse, but just in the English language and something you might talk about every day. Think about an example like P representing the statement, say, it is sunny today, right? And maybe Q represents the statement, I go for a jog, right? And so what information are we given here above that little deduction line? Well, we're given two statements, right? P implies Q is us saying that if it is sunny today, I'll go for a jog. And what other information are we given? We're given that not P implies Q, right? What does not P implies Q? It's us saying, you know what? Even if it isn't sunny, I'm still gonna go for a jog. All right. I just really want to go for a jog today. Right? If it is not sunny today, I'll go for a jog. Right? So if I know both of those things, right? P implies Q and not P implies Q. If it's sunny today, I'll go for a jog. And actually, if it's not sunny today, I'll go for a jog. What do I know? What is absolutely certain? What can I deduce from these two given statements? I have a 3-year-old. We started watching Dora together, and I now know even in a recorded video, you wait and after you ask a question for the audience to have a chance to respond. So what could we conclude? That's right, Q, exactly. So Q is what you can conclude. You conclude, I'll go for a jog, right? It doesn't matter if it's sunny or if it's not sunny. In either case, I know I'm going to go for a jog. So we can conclude Q, right? So this is a rule of inference. This is actually a famous rule of inference. You can write down lots of valid but not famous rules of inference. This one is famous enough that this has a name. This is called proof by cases, is the name of this rule of inference. And it's called proof by cases because we're analyzing all the possible cases of based on P, right? In the case where P is true, in the case where P is false, or you could say in the case where P is true, in the case where not P is true. Those are the two cases that we used, right? Either case led to Q, therefore we can conclude to Q itself from that. Now, here is, though, a nice, so this is, sort of witnessing a rule of inference that follows maybe pretty naturally from our intuition and the kind of discourse that you might have in the English language every day. One thing that's nice to do, though, is you can check that proof by cases, right? We can check that this rule of inference, you can check that this is valid using a truth table. And how can you do this? The way you do this is you want to take all of the given statements. So what we're going to do is we're going to take the first given, P implies Q, and you're going to AND it together with all of the other givens, which in this case, there's just one more, but there could be more. So here I have P implies Q and not P implies Q. Those are the two statements that I'm given. And I want to make sure that from P implies Q and not P implies Q, I want to make sure that that conjunction implies Q, right? So I want to check that this giant compound statement, P implies Q and not P implies Q, implies Q, right? That whole gigantic statement. I want to check that that statement is a tautology. And what does tautology mean? It just means always true. So I want to check that this is a tautology. So how can I do this? Well, it's honestly very similar to calculating an algebraic expression. If you're given some big algebraic expression, right? 2x plus 1 all divided by x squared minus 2 times parentheses, whatever you're given, right? What do? Well, you just sort of start working from the inside out, right? If you plug in something for x, you work on the innermost set of parentheses and then out, you go by order of operations until the whole expression is evaluated, right? We're going to do something very similar here, except we're not calculating quantities. Instead, we're going to be evaluating true or false based on all the possibilities for P and Q to be true and false, and according to the truth tables that govern these operations. So specifically, here's what I'll do. P, Q, and make a nice wide truth table here because we have a lot to do. So let's look one at a time at P and Q and the statements built from them. Now I'm going to start on the innermost sets of parentheses, right? So where I'm going to start actually is right here. P implies Q, right? I want to start with that operation. And that I just copy down from the truth table of how implies works, right? Implies is false only when the precondition is true, but the postcondition is false, right? Right. It's only false, say, when if you make a promise, right, and then you break your promise, right? If I am elected, I will not raise taxes. If you make that claim, what's the only way that you could lie? The only way you could be proven to be a liar is if you were elected and then you did raise taxes, right? The opposite of what you said you would do. In any other case, if you either stuck to your promise or if you just weren't elected, no one can say you're a liar. So, well, they could, but they can't prove you're a liar based on your actions. So this is our first column, right? That's that P implies Q. What would I do next? Next, I would do the not P. So I'm going to focus on this expression right here, right? And the not P, you could write it how I wrote it there. You could put an extra set of parentheses just to show that the not goes with the P and not with the whole implication. Either is fine. If you don't put the parentheses, that's what the default meaning is anyway. So let's put not P here, right? So not P, I have false, false, true, true. And now I'm ready to do not P implies Q. So this is where it takes a little bit of concentration to keep track of what exactly is happening. We're doing not P, so this column, right, this orange, and we're doing an implication with Q. And where is Q? Q lives over here, right? So I'm doing I'm going to use this column for my post condition and this column for my precondition, right? And that's where it takes a little concentration because the arrow is going to the right, but the column physically that you're implying to is to the left. So you just need to sort of be a little bit mirror imaged, right? What are we watching for? We're watching for an implication can be false. It's only false when not P is true, but Q is false. right? That's all we have to watch out for. So I go through the not P column. I say, what do I need? I need to look for when is not P true, but Q was false. That's the only way I can get a false in this column, otherwise true. So there's calculating that implication. Next, I have an and to do. So I want to do the and operation on which two columns? Well, on the red column, right? I'm going to use these truth values, and I'm going to and them together with what we just calculated, right? This green column. So when I do this and operation, what do I have? Well, and is only true if both are true, right? So in the first spot and in the third spot, they're both true, right? But the second and fourth spot have at least one false. So that's the and operation. Now, final step is going to be to take this whole expression, which I now have a column for, P implies Q and not P implies Q, and do an implication with Q from that, right? So take that column that we just calculated, right? Take this column there and do an implication with Q. We already have Q. Q is our purple column way at the beginning. Right? So what do I want to watch out for? Once again, this is only going to be false when what? When this whole giant statement, not P, or P implies Q and not P implies Q. It's only false when that is true, but Q is false, right? That's what I have to watch out for. It's the only time it'll be false. Otherwise, I can put true. But look at what we have. When is this yellow statement true? Here and here. First row and third row. But in both of those cases, Q is true, right? So this never happens, meaning this is always true. And therefore, proof by cases is a valid rule of inference, right? So this is when up here, when I said always true, that's what I meant by always true, right? All four cases in our truth table, they all came out to be true for this statement, right? So this is a tautology, and therefore we know that proof by cases is a valid rule of inference. And this is, as you'll see throughout mathematics, this is a super commonly used proof technique, proof by cases. There are more proofs that I can think of that I don't know any other way to do the proof other than a proof by cases, right? This is a very standard technique in mathematics. So this is, this is our rule of inference, right? P implies Q, not P implies Q. Conclude Q. And how do you check it? You do the conjunction of all of the premises, right? The given statements. You connect them with and then you say implies, whatever the conclusion is. All right. So that's our example of a rule of inference. I want to now also show an example of an invalid rule of inference, a proposed rule of inference that turned out to not be a valid rule of inference. So here is a very common logical error that people make, not just in mathematics, sometimes in mathematics, but also just in everyday life. P implies Q, therefore Q implies P. So here we have just one given, right? Just one given statement, just one premise and one conclusion. So what would this look like, right? Let's check to see if this proposed rule let's check to see if this is valid, right? Is it valid to conclude Q implies P from P implies Q in general, right? Well, how can we check? Well, you want to check to see if the statement P implies Q implies the statement Q implies P, right? Check to see this statement, right? Is it a tautology? Is it always true? This is what we want to look for. So it's going to be very similar setup. Right, we still have 4 cases because we're working with 2 atomic statements. And what would it look like? Here, I'll go through a little more quickly because the process is very similar. So P implies Q looks like true, false, true, true. And Q implies P looks like what? See, now it's going to look like true, true, false, true, right? Why did I put that false in the 3rd row? It's because that's where we had true implies false, right? Because it's Q implies P. Now, what do I want to do? I want to see, do we have that P implies Q implies P is always true? Is that always true? And if we look, we get true, true, false, and true, right? So even just the fact that in one case, it ended up being false, it's not a tautology. It's not a valid rule of inference, right? And there's no partial victory here, right? You can't say it's a 3/4 valid rule of inference, nothing like that. Instead, it's just not a rule of inference. It's just not a valid rule of inference, right? So that's the issue here, right? We would say not a tautology, right? And so this is in fact, right? P implies Q, conclude Q implies P, right? Is not a valid rule of inference. And this sometimes is called a fallacy, right? If you attempt to conclude a statement from a different statement and it does not follow, that's called a fallacy, right? A logical fallacy. In particular, this is also a very famous fallacy, just like proof by cases was a very famous rule of inference. This is actually a very famous fallacy. This is called the fallacy of converse, right? Meaning that Q implies P does not necessarily follow from P implies Q, right? So, so if someone does that, if someone decides to conclude Q implies P from P implies Q, they have committed the fallacy of converse. So that's the name of this fallacy, and you can think about it. You could think about it in terms of just, again, not necessarily mathematical statements, but just everyday English statements. If it rains, then the ground gets wet. Sure, right? If it rains, then the ground gets wet. From that information, you cannot necessarily conclude that if the ground is wet, then we automatically know it is raining. Okay? There might be something else that caused the ground to get wet. The river flooded, the lawn sprinkler turned on, I spilled my I dropped my water bottle, right? There lots of other, right? My coffee is empty and I'm crying profusely, right? There are lots of reasons the ground might be wet. So just because you know that rain will cause the ground to get wet does not necessarily mean rain is the only way for the ground to get wet, which is what the second would imply, Right. So that's the fallacy of converse. Very, very, very common fallacy that you'll hear, that you'll see not just in mathematical context, but in everyday discourse. So, all right, great. So that's rules of inference and how to use a truth table to tell a valid from invalid. Thanks.